Okay, so at this point we've talked about lines and parallel lines and perpendicular lines and equations of lines. Now we want to kind of expand on that and look at a lot of different types of equations and functions. One thing I'll note, in your book on page 183, there's a list of 8 different functions: lines, parabolas, cubics, absolute values, reciprocal functions, things like that. I'm not going to make a video going over those because that would just be me standing here writing out the pictures in your book. So I'm not going to do that, but you do need to know all 8 of those functions. We are going to use those and to look at some other different things we care about. So you will see them here, but I'm not just going to stand here and list out the functions there. So just be aware of that. What we do want to look at is transformations of functions. Now we can use those as kind of a starting point. And the idea is, well, one of those functions, the parabola, f of x equals x squared. We know what the graph looks like. It's a parabola that looks like this. And the question becomes, how can I actually mess with that? For the sake of argument, if I have f of x equals x squared plus 2, or if I have multiple colors, f of x equals x squared minus 4, how does adding 2 or subtracting 4 change my function in my graph? And really quickly, if we look at it, right here, if I plug in x equal to 0, I get 0 squared, 0 plus 2, which is 2. So at 0, I get 2. If I plug in 1, at 1 squared, I get 1 squared, which is 1 plus 2, 3, which is like right here. At 2, I get 2 squared, which is 4 plus 2, 6, which is here. On the other side of the graph, at negative 1, I get negative 1 squared, which is positive 1, plus 2 is 3, which is like right here. And it's pretty obvious, this graph will be symmetric and it'll look like that. It looks like the original parabola just moved up. If I subtract 4, well, if I plug in 0, I get 0 squared, 0 minus 4, which is negative 4. If I plug in 1, I get 1 squared, 1 minus 4, which is negative 3. If I plug in 2, 2 squared is 4, 4 minus 4 is 0. This will clearly mirror itself on the other side. And again, it's pretty obvious. It's the exact same graph, just shifted downwards. And that kind of gives us the first transformation we care about. If we add or subtract on the end of our function, outside of our function, we have a vertical shift. A vertical shift up or down. So, suppose I have the graph, or the function, f of x equals x cubed plus 5. Well, all we say is the cubic graph. If you don't know it yet, it's in your book. The regular cubic graph looks like that. X cubed plus 5 will be the same graph, but it'll shift up 5. And it'll look like that. And now I can kind of graph a whole lot more graphs by taking the basic ones from your book and adding transformations. In this case, adding and subtracting at the end of the function. But there's a lot more transformations we can do, and we want to look at all of them. I'm clearly going to have to clean my board soon because I've been writing on it so much. So suppose we have this. F of x equals the absolute value of x minus 1. Well, I want to graph that. Let's see. The regular absolute value graph just looks like a V like that. So what is the absolute value of x minus 1? Well, if I plug in 0, I get 0 minus 1, which is minus 1. The absolute value is positive 1, so I'm right here. If I plug in 1, I get 1 minus 1, which is 0. The absolute value of 0 is 0. If I plug in 2, 2 minus 1 is 1. The absolute value of 1 is 1. It looks like that. And now I can plot a few more points, but I know what the absolute value graph looks like. And clearly if I connect the dots, there will be my V right there. So what happened? My original graph was here. This graph moved 1 to the right. And I subtracted 1 on the inside. So then if we think about it, if I have f of x equals the absolute value of x plus 4, if I assume this is a little bit logical, here, subtracting 1 on the inside moved my graph horizontally to the right. So if I add on the inside, it would seem logical that it would shift me to the left. If I check a few points, well, if I'm going to move left, I'll move left 4. I'll think about that. If I plug in negative 4 for x, I get negative 4 plus 4, which is 0. So at negative 4, I get 0. If I plug in negative 3, negative 3 plus 4 is 4 minus 3, 1. The absolute value of 1 is 1. If I plug in negative 2, 4 minus 2 is 2. The absolute value of 2 is 2. If I go to the left, say negative 5. Negative 5 plus 4 is negative 1. The absolute value of negative 1 is 1. And then sure enough, I see that V for my absolute value graph. So it would look like if I add or subtract on the inside of the function, inside the absolute value, I move horizontally. The one thing to keep in mind, normally subtraction moves me left. When I do it inside of the function, it moves me right. Addition usually moves me right. When I add inside the function, it actually moves me left. But what that really means is, now I can really start messing with my functions. Suppose I have y equals x plus 2 squared minus 4. I want to graph that. Well, all we say is, if I subtract on the outside, that shifts me vertically, so this will go down 4. If I add or subtract on the inside, this shifts me horizontally, and it's backwards, so plus 2 will go left 2. Now I just pick a point. For the parabola, I'll pick the vertex. The vertex was at 0, 0, but now I'm going to move it left 2, down 4, and then I'll just draw my parabola. And there's my graph right there. If we want to label the vertex, we went 2 left, so that's negative 2. We went down 4, that's negative 4. And there we go. And that's actually the goal here, to be able to look at a function and say, what's my starting function? It's x squared. How did I move it? That shifted me horizontally, that shifted me vertically. There's my graph and I'm done. There's still a few more transformations we want to look at. So, suppose we have y equals 5x squared. Well, let's see. I won't draw the basic parabola again to start because we know what it looks like. But if I plug in 0, I get 0 squared, which is 0 times 5, that's 0. If I plug in 1, 1 squared is 1, 1 times 5 is 5, so I'm up here. If I plug in 2, 2 squared is 4, 4 times 5 is 20, and I'm like way up there. We know this graph is symmetric, so it's going to go way up there. And the question is, how did that change my original graph? There is actually a trick to this, an understanding of the transformations. Essentially, every operation I do inside of the function or outside of the function. The one we just looked at, x plus 2 minus 4, and that was squared. The plus 2 is inside of the function. It's inside of the square. The minus 4 is outside. And the way it works is, this affected me vertically. It shifted vertically. This affected me horizontally. And that trick holds for all transformations. If I do something inside of my function, it will affect my function, my graph, horizontally. If I do something outside of my function, it will affect my graph vertically. So here, this is the square right here. That 5 is outside the function, which means it should affect my graph vertically. And what we actually call this then is a vertical stretch. Essentially, I took my original parabola, yanked it vertically, which thinned it out. It stretched it. It made it get bigger faster. But by the same token, if I have y equals 1/2 x squared, well, if you think about it, if you multiply things by 1/2, they get smaller. And there's a trick here. If this coefficient out in front, we'll say y equals a f of x for any function f. If a is greater than 1, it's a vertical stretch. It gets bigger. If a is between 0 and 1, it's a vertical compression. It gets smaller. Essentially, in either case, I grab my graph and I either yank it this way and stretch it, or I compress it downwards like this, which flattens it out. So that this graph will flatten out. Which again, makes sense. If I multiply things by 1/2, they get smaller, they don't get big as quickly, they spread out. And again, the key component is, if I do something outside of my function, I affect my graph vertically. If I do something inside of my function, I affect it horizontally. Which means, I think we have time for one more transformation in this video, really quickly. If I have y equals 5x squared, now we see the 5 is inside of the square. If I just plot a few points, at 0, 5 times 0 is 0, 0 squared is 0. At 1, 5 times 1 is 5, 5 squared is 25. So that's way up here, and I'm going to run out of board space. This will be symmetric, so it will look like that. And the question is, what did I actually do? From a visual perspective, that looks like I grabbed my graph and stretched it vertically. From a math perspective, this 5 is inside of the function, which means technically I did not affect it vertically, I affected it horizontally. And essentially, this is not a vertical stretch. I affected it horizontally. I actually took my graph and pressed it in this way, which made it get thinner. I can also grab it and pull it out that way, which will make it fatter. The understanding of that is pretty clear. The wording can be confusing, because if you think about it again, from a vertical perspective, I stretch it this way. From a horizontal perspective, to make it thinner, I actually have to compress it this way. So here we say, if I have y equals a f of x, right the way your book does, y equals f of ax, if my a is inside the function, if a is greater than 1, it's a horizontal compression. If a is between 0 and 1, it's a horizontal stretch. From your perspective, you just need to be able to see the graph, recognize what it looks like, and if the terminology is a little bit off, I am okay with that for the purposes of what we're doing. I care about the understanding of the graphs. There's a few more transformations we want to do, so I'll make another video for those because this is long enough, and then we'll actually look at a bunch of examples.